So lesson number 4, and we're going to compare graphs of linear motion. Okay, so 2 essential learnings for this lesson. The first of which is that the area under an acceleration time graph is the velocity of the object. Okay, so that's the first. We're going to look at acceleration time graphs in the first half of this lesson. And then the second essential learning is that if we're given any one of the 3 motion time graphs, right? So either if we're given a dt graph or a vt graph or an at graph, then it's possible, and we should know how, to construct the other 2 using data that's found in the original. Okay, so let's look at acceleration time graphs first. When dealing with uniform or constant acceleration, these graphs will always be a horizontal line. Okay. And in fact, in high school kinematics, in grade 11 and 12, we're only going to encounter situations with uniform acceleration. So for the most part, these graphs will almost always be a horizontal line. Okay, so launching right in, here's an acceleration time graph for a lion. You'll notice axis is labeled and we have a direction because acceleration is a vector. And so if I read the graph, I get instantaneous values of acceleration. And as an example of this, I could say at t equals 2 seconds, the acceleration is 9 meters per second squared. East, of course, this is pretty straightforward because if I look anywhere along this line, the value is 9 meters per second east because it's constant acceleration. Okay, a little bit more interesting perhaps is the area underneath. Area here gives velocity. Okay, so this is important that the area tells us information about velocity. And so let's take, for example, the first 4 seconds. So what velocity are we talking about? Well, we're going to look at the first 4 seconds, 1, 2, 3, 4, and this is then the area that we're talking about. Okay, so as an example, velocity is equal to, of course, the area that's underneath, so we get length times width, right? And the length of this would be, say, 4.0 seconds, multiplied by the width of this. Well, we said it's the same everywhere, it's 9 meters per second squared. And if we look at these 2 numbers, 4 times 9, we get 36. And if we just do a quick check of our units, seconds, meters per second squared, one of these goes away. And yes, indeed, we get units for velocity. We can put the vector symbol on there because a time is not going to change our direction, and we get 36 meters per second east. And this is what we're talking about. This is kind of how we're going to find this area at different amounts of time. Okay, so we could do the same thing. We could say find the velocity at 6 seconds, and then we would simply track over and we'd say 9 times 6. We could say find the velocity at 2 seconds. We could do that in exactly the same way. All right, so given now that we know how to work an acceleration time graph, let's consider a few other interesting things. Velocity time graph and a few different velocity time graphs, and we're going to kind of show a few acceleration time graphs here. So first thing is, let's investigate a velocity time graph that is horizontal, so a horizontal VT graph. This means that there's no slope, and of course we know that on a VT graph, if I want information about acceleration, I take the slope of it. So this gives me a 0 acceleration situation. And that's okay, because what that means is that we've got constant velocity, right? That's exactly what that curve showed us. We've got constant velocity, and that means no or zero acceleration. An example of this was the physics buggy that we used on one of the very first days of class, right, where it had a constant velocity. And we noticed that its motion was very uniform, is that it went in a straight line with one constant velocity. So that was an example from class that we used that would produce a VT graph and an AT graph just like this. Okay, so let's look at something a little bit different then. Let's look at a VT graph that's increasing, right? So we've got a positive slope in this case, so that means our acceleration time graph will be positive. And what this means for us then is that we've got an increasing velocity, and this is a positive acceleration. Okay, and a good example of this would be our wind-up truck or Jeep, right? That we would have used, and we should be specific. We should say the beginning of the motion had an increasing velocity, because we did see that later on it slowed down, but we're not going to talk about that. That's a little bit too complex. Okay, last but not least is a decreasing velocity, which you probably would have guessed, and of course that would give us a negative acceleration. And so what does this look like? So this is a decreasing velocity, and a negative acceleration. And one thing that we should probably point out is that we've called this a negative acceleration and not a deceleration, and that's an important distinction to make. One of the things that sometimes is a misconception about the word deceleration, or sometimes that what deceleration tends to imply, is that something will slow down and then come to rest. But that's not always the case with negative accelerations. Yes, deceleration means, slow down, come to rest. But very often we have negative accelerations, which means that something, yes, will slow down and come to rest, but will be continuing to accelerate in that direction, so it will simply turn around and then go back the other way, which is exactly what this object does. This object here has a decreasing velocity, and eventually, yes, it comes to rest for an instant, but then its velocity keeps on decreasing, but it's decreasing in the opposite direction. So this is actually slowing down in the east direction. It comes to rest, and then it starts to speed up in the west direction, which is one of those finer points about VT graphs that we need to be aware of. So something that we've done in class that acts as an example is actually Bungee Barbie. And one of the reasons why this serves as a nice little example is that on her way downwards, Bungee Barbie was decelerating, or we should say very specific, she was slowing down. So she had a negative acceleration. And we could say that she was decelerating, but she didn't come to rest at the bottom. She came to rest for a very, very brief instant and then sprung back upwards because that elastic band pulled her up. So she had a negative acceleration and her velocity changed direction. Which is an important distinction, okay? All right, so now that we've been looking at some graphs, let's continue on with some graphical analysis. As you're going to see, this is very, very, very tricky. Okay, so this is one of the more complex parts of our unit. And before I begin with this, there's two things that as soon as you're done this lesson, I'm going to write it down here. There's a place where you need to go. So in your textbook, on page 33 and 34, there are two tutorial questions. And these are very, very helpful. Okay, so I would strongly recommend that you take a look at these when we're done here. So we're going to take this velocity time graph and we're going to convert it. But let's talk in general. Let's just do a little recap because there's a little infographic here. Is that when I have a DT graph and I want information about velocity, I take the slope. Okay, so we know that. DT graph, if I want information about velocity, I find the slope of that. Same thing, if I have a VT graph and I want information about acceleration, I take the slope. Okay. In the same way, if I have an acceleration time graph and I want information about velocity, as we just did above, we find the area. And if I have a velocity time graph and I want information about displacement, I find the area. So this is kind of like our general overview. Now let's do an example where we're going to see how tricky this is going to be. Okay, and I'm going to go through and I'm going to kind of show you in a step-by-step process what I'm going to do. And I'm going to try and move rather quickly. I'm going to do the first little bit of this graph and then I'm going to leave the rest for you to do. So the first thing that we want to consider when we're doing these types of questions is that we want to break our graph up into segments. So you'll notice first and foremost is that I've laid the graph for my displacement time graph, which is what I'm trying to create. I've laid that right below the graph of my VT. And so very often when you're doing these problems, you should do them on graph paper, one right below the next. And what that does is it means that my scale is going to be exactly the same because one square up here is equal to one square down here. And I don't have to worry about any of these, any scaling problems, okay? So this is confusing enough without having to worry about that. So let's break this up. There's a whole bunch of different points, and we're going to break this up into segments. So the first point when we look at this is that we're going to look at the beginning, and we're going to take information at the beginning. Then we're going to go to this point where it crosses the axis. We've got a velocity of 0 here. And then we're going to come up here and we're going to consider this. And then last but not least for us, we're going to consider this. And then I'm going to have you work on this part of the graph after this is all done and we're going to see what you get. But we're going to do this part together. And so what we can do now is we can transfer these points down to our axis down here. So we had 1, and then we had 2, and then we had another 2, and then we had 3. Okay, so we've got 2 units of time, 2 units of time, and then 3 units of time. And that's exactly what we had up here. So all we've done is we've just kind of kept track now down here of where these different points are. Okay, so what we want then is that the first thing we want to do is that if we've got a VT graph and we're looking for information about displacement, we know that we're going to find the areas. So we've divided the area into sections, and so now what we want is that we want to consider each area that we're going to find. So here's the first one. And this area right here, underneath this, we notice right away this is negative, right? So we've got a velocity that's increasing, but it's increasing in one direction, and we've got a displacement that's negative. So this graph is going to become much more negative when we draw it. So because we've got a negative area. That's in contrast to this section right here, which is the next one we'll draw. And this part of the graph is, of course, it's got a positive area. So we're going to go from displacement that's getting more and more negative to now a displacement that's getting more and more positive. And finally, this last section that we're going to draw, this one up here, this is also positive. So you can see that when it's above the axis, it's positive. When it's below the axis, it's negative. Okay? So that's the first thing. So our graph is going to start out by getting more negative down here, and then later on, it's going to get positive. In this section, it's going to get positive, and then this section, it's going to get more positive. Okay, so that's kind of a little cue for what we're going to do. All right, now that's one of those first things that we've looked at. We've looked at displacements. Now we need to look at the type of graph that we're going to sketch. Are we going to draw a curve? Are we going to draw a diagonal line? Or are we going to draw a horizontal line? And what we know, this is another little clue, is that we can kind of make a note up here, is that we know that diagonal lines on VT, this tells us something. This tells us we get curves on DT. Right? So diagonal lines on VT, and we get curves on the DT graph. So it means that this section here, when we take a look at this line right here, that's a diagonal, so we're going to get a curve down here. This right here is a diagonal line, so we're going to get a curve down here. What about this section? This section right here is a straight horizontal line, which means a constant velocity, and so that's going to tell us something else, right? So when we've got horizontal lines on the VT graph, that tells us something. It means that we're going to get diagonal line on the DT. So that's another important piece of information that we're going to have. We're going to look now for, because we know what these shapes are going to be. So we know that we're going to have a curve, and then we're going to have a diagonal line. So that's kind of like, what does the shape of the graph tell us? Now we want to look at, okay, so where do we start? So first of all, we're going to assume right here that a negative velocity at 0 time. We're just going to assume that this graph starts at a displacement of 0. And that's okay to do in this case. Assume we start at displacement equals 0. So that's okay. We've already got a dot there, and that's where we're going to start. And then what are we going to do? Well, do we start with a flat line? Do we start with a curved line? Like, what do we start with? And we notice that right here we have velocity that is not 0. And so what that means is that we're going to start with a line that is not equal to 0. And we know it's going to be a curve. So now we come up here and we say, okay, well, that's how we've started. Now how do we finish this little segment? And we come to this and we say, okay, well here, this is a velocity that if we look right here, bing, 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 this is equal to 0. So that means that the slope of this line has to go from a slope right here that's not 0 to a slope right here that is 0. And it's pretty straightforward how this curves now. We come down here, we go right there. So we've just drawn our first little segment on this graph, no problem. We drew it in a direction that honors this. It got more negative. We now know what's going to happen in this section. It's going to get less negative. So now we need to get from where we're at to we need to get to our next point. We know that it's going to be a curve because the diagonal on here is a curve. We know that it's going to get more and more positive. And so what we do now at this point is we say, well, we started here and now we're going to start increasing our velocity because we had a velocity right here. We went to 0, so this was a decreasing velocity. And now we have an increasing velocity. Our velocity is getting more and more positive. So we're going to curve up until we get here. And now the line, we're still going to get more and more positive, but now we continue along at a constant velocity for 3 units, and we're going to maintain the exact same slope that we had at the end here, and that's where we end. And so now at this point we say, okay, well, hey, look at what we've got. We've got this curve. It's kind of gone in a certain direction. We came down, we had a displacement downwards, then we displaced up, now we've displaced up. We've got all of the important points that are listed, and at this point I'm going to say you can go ahead and from this point on, so from here onwards, you can try your hand at finishing off the rest of this, okay? And then we'll take this up tomorrow.